Okay, this is our introduction to lesson 3.5 in geometry, and the topic of this lesson is called angles of polygons. And this is one of those sections where we do have a few things here that you'll need to write down, as you'll use those quite a bit on assignments and on quizzes and tests. So just label your notes with the topic of angles of polygons. Now, the first thing that we're going to talk about is what is a polygon. Now, a polygon, there's kind of four parts to that definition. So as I go through these, write these down. Now, one thing, the word poly means many. So simply, a polygon is a many-sided figure. So I could have a three-sided figure, I could have an eight-sided figure, and so on. Also, some other characteristics of a polygon is that the figure needs to be closed. So for example, I cannot have something that might look like this, because that's not closed. I kind of have a gap in that figure. Something else a polygon has to have is straight sides. So in other words, if I had something that looks like this, and all of a sudden a curved end to it, and then something like that. So that would not work, because I don't have all straight sides. And lastly, the figure needs to be simple, and nothing complex. So in other words, I can't have any sides that cross, something like that. So a polygon, it's a many-sided figure, it's closed, it has straight sides, and it's a simple figure. All right, now, once we get into polygons, we can categorize polygons into two categories. One is convex and the other one is concave. Now, let's give an example of these just to define these. Now, convex, for example, if I made a rectangle. Now, it's convex if I can place 2 points any place, connect them, and that segment is inside the figure. So in other words, I can put 2 points any place in this figure, connect them, and the segment's inside the figure. But, for example, say I have something that looks like this. Now this figure would be, let's see, 1, 2, 3, 4, 5 sides. So this is called a hexagon. Now I can put 2 points right here and connect them in the segments inside the figure, right? But if I put 2 points here, notice that the entire segment's not inside the figure. So notice the difference between convex and concave. Another way to remember this is concave. There's probably a part of it that kind of caves in, hence the name concave. Now, different types of polygons. And you've had these before here, but let's review them. So again, write this down. Make sure that you wrote down convex and concave, an example of each, and also explain how you would place the 10 point, or the 2 points, I mean. So you should be able to put 2 points any place, connect it, and the segment is inside the figure. All right, now, three-sided figure, we call that a triangle. Four-sided figure is a quadrilateral. A five-sided figure is a pentagon. A six-sided figure is a hexagon. Eight-sided figure is an octagon. 10 sides, decagon. And on all these here, notice the prefix. The prefix stands for the number of sides. So tri means 3, quad means 4, penta means 5, and so on. And this is how they come up with the names. Now really from this point on, there are specific names for an 11-sided figure and a 12-sided figure, but we don't see them or we don't use them a whole lot. So if we have a 15-sided figure, we would just call that a 15-gon. Or a 20-sided figure would be a 20-gon. And the reason for that is it just makes it easy to define them. Okay, next thing. Take a moment and just make a copy of these diagrams. Now that you have these copied down, let's see what type of diagrams I have. Now this is a quadrilateral. And certainly I can be more specific on this. This would be a rectangle. But with these names that we gave a little bit ago are very, very general names. Let's see, the red one, 1, 2, 3, 4, 5, 6. So that's a hexagon. And then I have a pentagon down here. Now, we're getting to this thing with diagonals. Now, what is a diagonal? A diagonal is simply a segment that connects one angle to another one. So, for example, this would be a diagonal. It's connecting one vertex or one angle to another angle. And really, I should define it as connecting the vertices. I cannot go just straight down like this because you're just connecting corners. So a diagonal actually goes through the figure. It cuts through the inside of the figure. So notice there that in the quadrilateral, that's a diagonal. In this one, now here, let's go back to the rectangle. Now, when we're talking about, you've been taught in the past that if I added up the 4 angles in a quadrilateral, what do they add up to? We know in a triangle it's what? The 3 angles add up to 180, right? So these add up to 180, the inside angles, right? How about a quadrilateral? Well, they add up to 360, and here's the reason why. Because when I drew this diagonal, I actually have 2 triangles. Well, for each triangle, remember the 3 angles add up to 180 degrees. So therefore, 180 and 180 is your 360. Now, I could use that same idea for our pentagon. So there's a rectangle, there, I could draw my diagonal there, and I have a triangle on the top, and then I could draw another one. And notice I have 3 triangles, and for every triangle I have, the 3 angles add up to 180. So my 180 times 3 is 540. So when I add up the angles in a pentagon, 5 of them, right? Because if I have 5 sides, I have 5 angles. They add up to 540 degrees. Again, 4 sides means you have 4 angles. They add up to 360. Now you can do the same thing with your hexagon. You can split it up. And there's a number of ways you could split it up, and you could keep on doing that. Now, the whole problem here is if I'm trying to figure out the sum of the interior angles. The sum of the interior angles for a quadrilateral was, what again? 360. The sum of the interior angles of a pentagon was 540 degrees. How about if I had a 20-sided figure? That might be pretty hard to do by just splitting up into a bunch of triangles. So, we make it a little easier. And I want you to pause this and write down Theorem 313. Now, Theorem 313 says the sum of the measures of the angles of a convex polygon, and really we should say the sum of the measures of the interior angles, so I want you to add that, of a convex polygon with n sides. N sides stands for how many sides it is. And we're going to use this formula. So for example, let's take that rectangle we had before. Remember, we got 360 degrees for that, didn't we? And we'll try to write that. There we go. All right, so 4 sides here. Put that in for n minus 2. Do your work inside the parentheses. And 2 times 180. And notice we get our 360 degrees. Now for, how about our pentagon? I take our formula up here. Since a pentagon has 5 sides, take 5 minus 2 times 180. So I would have 3 times 180, which is 540 degrees. And that's what we got before, right? For our hexagon, 6 sides, I take 6 minus 2 times 180. 6 minus 2 is 4 times 180. What do we get? 720 degrees. So when I add up all 6 angles, I get 720 degrees. So this is a convenient formula, and this is a formula that you'll use quite often here in this book. Okay, pause this and write down Theorem 314. Now, Theorem 314 says the sum of the measures of the exterior angles of any convex polygon with one angle at each vertex is 360 degrees. And we've already talked about this a little bit. So let's look at our exterior angles to our blue rectangle. So if I extended this line, I've got an angle 1. Let's call it there, angle 1. And if I extended this side, maybe I have an angle 2 there. Extend this side a little bit, an angle 3, and extended this side, and I have an angle 4 there. And that's why they said one angle at each vertex. Now if I added angle 1 plus angle 2 plus angle 3 plus angle 4 there, I'm going to get 360 degrees. Let's go down to our pentagon. With one, let's extend the side so I have exterior angles. And it doesn't matter which side you extend, just so you have one angle at each vertex. Angle 4, and finally I'll extend to this side an angle 5, right? Well, if I added angle 1, 2, 3, 4, and 5 together, I'm going to get 360 degrees. Same thing with our hexagon. So any type of figure, it's always 360 degrees for the exterior angles. All right, last thing. Polygons can be, and there's three things that polygons can be. They can be equal angular, meaning all angles are equal. They can be equilateral, meaning all sides are equal. Or they could be what we call regular, where all angles are equal and all sides are equal. So make sure you have this written down.
Please. I have a college representative from the University of Minnesota here in the guidance office at this time. If there's any students that are interested, please come to the guidance office.
Okay, now an example of each one of these would be, let's use a hexagon. Now, let me change the color here. Let's say that I have, I'm going to try to just freehand this. So there's one side, two sides, maybe 3 sides, 4 sides, 5 sides, 6 sides. Now it doesn't look like any of the sides are equal, and it doesn't look like any of the angles are equal. So that would be none of these, right? Not equal angular, not equilateral, not regular. Now, how about if I took, if I made my same hexagon, but I made it maybe like this, or to the best of my drawing ability, maybe something like that. Now, I've tried to make it so that all the angles, maybe around 120 degrees, where all the angles are equal, but certainly all the sides don't look like they're equal, do they? So this would be equal angular. How about if I made a hexagon that maybe looked like this? Now I'm going to try to make all the sides equal, or look like they're equal. Not quite, is it? So we'll go to about right there. And maybe something like this, where all the sides are meant to be equal. 6 sides. Now it doesn't look like all my angles are equal. So in other words, this one was none. This one was equal angular. This one would be equilateral. All sides are equal, but not all the angles are equal. Now if I made a hexagon where I meant all the sides to be equal, maybe something like that. Like so. Where I mean for all the sides to be equal, and you kind of get the idea, and all the angles are equal, right? This would be an example of regular. So we can also categorize polygons with these 3 terms. Okay, so again, the topic of lesson 3.5 was angles of polygons, and make sure you have the notes on these.